That's it. Okay, good morning. This is Lois Gray, North Highland College. This is your control and instrumentation class. I'm not exactly sure which week. We think maybe about week 6. So I don't think anybody will be seeing in, but as usual, this will be recorded, so you can look at it later. Right, guys, so I wanted to ask you what you wanted to do today, because what I was going to do was the PID control lecture, because that's relevant to your coursework. But if you've already done that bit in your coursework, then perhaps we could just skip that one altogether and go back to doing something more relevant to the exam. It's your choice.
Skip that too, eh?
The PID one, John, you were wanting a quick class, so it's quite a short class. Were you wanting a quick class? Yeah?
Yeah, quick class.
Yeah, so the one about controllers would be quite a short lecture. The one about block diagrams probably a wee bit more involved. We can always catch up anyway, because the instrumentation stuff's quite easy, and I can do 2 classes 1 week covering that. So I could do, for instance, the intro to that and the temperature sensors in 1 class.
So what for PID is?
So will we go for controllers, or how many people have finished the controllers part of their coursework, done the tuning and got their system working and everything?
I've tuned it over.
You have tuned it?
I've tuned it over.
Using the ultimate cycle method or the process control method?
Process control method.
All right, okay.
Does that know what you want?
No, that's fine if that's what you've done. You know you have to do that open loop.
Yeah.
Yeah.
Open loop.
So you've done that. Has anyone else finished that bit?
I couldn't get my process control to work.
Well, it might be worth. Is it worth me doing this lecture with you, or have you all watched the videos and you're all quite happy with everything that you've learned so far?
What do you think?
How many people would like to do the controllers
I will do control
lecture? You want to do it?
Yeah.
Is there anybody who doesn't want to do it? No. Okay. You might not learn very much though, because you might have already done it. I suppose it's a bit of revision for you, if nothing else. Then. You happy with that? Yeah.
You want to take it or you want me to take it?
You want to take the class? Yeah, you can take the class. Usually I can't even get people to come right over it. So, yeah, okay, I haven't really prepared, but I mean, I know most of this stuff anyway. Right, we'll switch over. So we're doing, you can see on the computer here, week 5 lecture for controllers. We had actually already done the week 6 one, which was the frequency analysis stuff. We did that just before we left. So what's left after this is the block diagram models in the control side. Block diagram models, which I would say is quite mathematical, quite a lot of algebra, but in some ways intuitive, because it's just moving blocks around, so not terribly difficult, but not really relevant to your coursework, more relevant to your exam. And then we also have the stability and steady state errors, which is like a completely separate subject almost, so it's a wee bit more tricky, mainly because it just doesn't kind of follow the same flow as the rest of the things, and again quite a common exam subject. So we've got those 2 left in control, and then there's about 5 or 6 weeks worth of stuff in instrumentation, but as I said, I can compress that and maybe join some of the lectures together, because firstly most of you are electrical, certainly sitting here, and you know a bit about sensors and transducers already, and probably about instrumentation systems. I mean, some of you are instrument techs, so probably know more than me. And secondly, it's not as difficult a subject as the control theory anyway. So if everybody's happy, we'll just get started on the controller stuff today. So I haven't actually looked at this PowerPoint, but I'm hoping it will. I'll show you the GIF later on, but let's start with the PowerPoint first. So you should be pretty much finished your courseworks by now. You've got till the end of this week, I think. Or is it Monday?
Monday.
Next Monday, yeah. So I would hope that you would have done most of the work on the system, so all the open loop stuff, and made a start on the PID closed loop control system as well. And then just leaving you to do the frequency analysis calculations and Bode plot for the rest of the week. But I guess everybody will have their own schedule. But that's where I would expect you to be. Would be just starting the frequency analysis stuff. Especially given that your original deadline was earlier. So I've had a few queries from the remote students. Of course, if you've got any more queries, guys, I'll just switch back to camera. You can just phone me or email me, as you've been doing. I should be back now for most of the time, so you'll be able to get hold of me a bit easier. Right. Let's start this then. still a bit jet lagged, I think. I only got back on Sunday. So. I'll switch the lights on. It was quite interesting trying to teach the kids how to do coursework 1 and 2 without any computer software. That was really quite tricky. I had to draw everything on the blackboard. I don't think they understood much of it. It was really their fault. It was my fault. Well, whoever was setting the room up. Right, so we've got a number of different controllers. So the whole point of this course is to learn how to really kind of design, tune controllers and appreciate their uses. So there's a whole load of different kinds. You've got your basic two-position or on-off. They're actually slightly different. So on-off is obviously on or off. Two-position is similar to on-off, but it may not necessarily be totally off. It could be on and on at a different level. So that's the differences between two-position or on-off. Most you'll have come across on-off type systems. Your heating in your house probably is an on-off system. Trying to think what else there is. Obviously, there's quite a lot of open-loop systems that are on and off, like toasters and kettles and things. But some kettles nowadays are probably closed-loop. And then you've got PID, which is the most common industrial one. I'm not terribly sure why, but I know it was invented way back in the sort of 40s by a couple of guys then, and it just seems to be. I suppose it's because it's the most tunable, it's the easiest to tune, and the most adaptable. And then some of the more recent, because of the advance in computer technology, some of the more recent ones are coming very much to the fore now. You've got your adaptive ones, which are used on things like planes, because you can imagine if with a plane the environment's changing so rapidly, there's so many different things going on that just having a set PID, tuned PID controller wouldn't necessarily be good enough. It's got to be able to cope with different weather conditions and temperatures and pressures and all sorts of things. So the likes of your adaptive controllers are quite good for that, because what they do is they have quite high processing power, and they actually adapt to the environment. So the tuning parameters are constantly changing depending on feedback and what the controller believes it should be doing. So they're pretty clever. They kind of fall into the same category as these. So some of these neural networks and genetic algorithms are used for adaptive controllers. They're very mathematical. If you go on to do the new degree, I think there's an honours module which covers more advanced control theory, but there is quite a lot of maths in it. It's quite a mathematical process. Because that's how computers work. They work on mathematical things. Fuzzy logic is quite fun. We used to do that in this class, actually, but then for some reason it got removed. I think the external examiner said it was too much in one course, so we got rid of that. But fuzzy logic is actually, it's not really particularly mathematical. It's based on, it's called fuzzy logic because you know logic is normal 0 or 1. Well, fuzzy logic is still digital logic, but it's different levels of zeros and ones, if that makes sense. So you can have something halfway between a 0 and a 1, so it's fuzzy. Using Simulink for that's really I quite enjoyed that. There's lots of pictures and things, and I quite liked it. But anyway, we removed it now. I don't know how much that's really used in real life. There was a whole heap of technology came from Japan with fuzzy logic printed on it, but I don't know whether it was really fuzzy logic or it was just a selling point. Probably just a selling point, as it's like. I can't see why you would need fuzzy logic for a washing machine, for instance, which is what this photo is. And then the two other ones are very mathematical methods, again, neural networks and genetic algorithms, and they're what's used in your artificial intelligence, so your robots and complex pieces of advanced electronics. Tend to use these two. And I did a course in them at Dublin City University, and again, it was really interesting, but very mathematical. So, quite fun. If you like maths, it's quite fun. If you don't like maths, not at all. Anyway, so we're only going to really be looking at, very quickly, the two-position, and then concentrating on the PID. That's the two that you need to know for the exam and for your course reference. We're not going to look at the others. So that's an example of how the two-position works. Obviously, two-position is cheap and simple, but there's also a big error band where there's some variation. So, for instance, a temperature controller, you might be trying to keep your room at 20, and effectively it's probably going to go from something like 18 to 22. because there's a big error band. Most people who sit in this room know that that's the case because this room is never at the right temperature. So the controller for this is not great. So the idea is it could be an on-off type like this one. What's happening here? This is a temperature. Temperature is a good example of this because it's very common on a control system. You can see as the temperature goes up, the heating's on at this time, and then when it reaches a certain point, it goes off, and of course the temperature cools down until the heater comes back on again. That quite obviously makes sense. This area from here to here is called the dead band, so that distance. And you can vary that, obviously. You can make it more accurate if you wish, but there's advantages and disadvantages to having big dead bands and small dead bands. So obviously with a large dead band, you've got a big range before the heaters come on and when they go off again. So you've got a big inaccuracy there. So if you make that smaller, that's fine. But the problem with making it smaller is you've got things switching on and off much more rapidly. So for instance, if it was a flow type system, you'd have valves possibly chattering on and off at a very fast rate. And sometimes that can be quite damaging for the equipment. It doesn't really like to be switched on and off because it's two extremes at a fast rate like that. So, that's, I suppose, the disadvantage. Also, you get noise. Some of you might have heard valves chattering in your heating at home, and that's caused by that, like fast on and off switching. So that's it really. That's all there is to on and off for two-step controllers. Any questions about that? It's quite easy to understand, I think, isn't it? Right. Okay. And then we come to our PID. So you can do PID, obviously nowadays you would just buy a PID controller, but you can actually design it from scratch using some electronics components. And actually this is a good introduction to some of the instrumentation stuff, because we use these op-amps a lot in instrumentation as well. So it's made up of three controllers in one, really, and you can use any combination of them separately. You don't have to have the full PID, and in fact full PID is quite difficult to tune, quite sensitive to noise, and generally not really used as the full complement. But you obviously need to learn about all three to know whether you need all three or not. The proportional one's fairly straightforward. That's just a gain. So the controller multiplies. In fact, I probably should just show you that. We'll go back to that for a minute so that you know what we're talking about here. Block diagram. I don't know why the slides don't do this bit, actually, to be honest. I'll draw it like as if it's a Simulink. Usually that would be a circle, but I'll draw it this way because you'll have seen this in your notes. And then you have your system, which I think most of you have modelled in the Laplace domain for your coursework, haven't you? Most of you got like a k over st plus 1 type equation. Yeah? With your like notes.
Your transfer function.
Yeah, your transfer function. Yeah. Okay. Well, that's in the Laplace domain, that transfer function. You can get them in the time domain as well. So you might have a system. I suppose, strictly speaking, there might be some transfer function for the sensor, feedback path as well. Anyway, so the idea of the controller is you put your reference input in here, and you're trying to get your controlled output to be equal to your reference input. So again, temperature is probably the easiest one to think of, but so you might want us, I don't know, 20 degrees here. The idea is you get 20 degrees here. And what happens is this feedback path's measuring the actual output temperature and just feeding a small amount of that back through a sensor. Okay, so that would be a sensor. This would be your system. This is your controller. And the error detector, which is this part's looking at the difference. Yeah, I think mostly we've done this in system analysis at some point. So the error detector is just a subtraction element, but it's looking at the difference between what you want and what's being fed back. Of course, this must be negative. Why must that be negative? What happens if you put positive feedback into a system? No answers. Nobody knows. What happens to a system if you've got positive feedback? It's very bad, for a start. It becomes unstable, yeah? Your system. We did this in the frequency analysis stuff I did with you just before I left, where we were looking at Bode plots and gain and phase margins, and yeah, and remember I said if you've got 180 degrees phase shift on your output and you feed it back, that gives you 280 degree phase shifts, and then your signal adds, so you end up with an unstable system, because rather than subtracting from the input, you're adding to it, and that's obviously going to make the error get bigger and bigger and bigger. It's going to make the output do that, yeah, unstable. So you always have to have negative feedback. The only time you'd ever have positive feedback is if you're trying to design an oscillator in electronics. Oscillators have positive feedback because you want them to do that. That's the whole point of an oscillator. But that's the only time you would ever have positive feedback. Okay, so just try and remember that. Feedback always negative. Must always be negative. So, yeah. So we've got a subtraction here, and what happens at this point is you end up with the difference between what you want and what you are getting, which becomes an error. And then the idea is that the controller will see what that error is, and it will drive an actuator in your system to try and drive that error down, to try and make the error disappear. What's the actuator in your system, in your coursework? I haven't really covered actuators, but I'm sure you know what they are. What's the actuator in your system? What's the controller driving? I mean, I know you're doing it on Simulink and it's all maths and blah, 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 but it is based on a real flow system, so what's the controller controlling? Yeah, the pump, yeah. So in your case, your actuator is your pump. And of course, your sensor is your level sensor, yeah. So in your case, it would be the level. So these things are within the system. That's in the system, and that's in the system. This is the thing you're adding separately. So with a level control system like we had, you'll see the error here in the PID system. The idea is that if that's a big error, it'll make the pump drive harder to try and remove the error. If it's a small error, it might scale down the volts it applies to the pump. If it's a positive error, so if the tank's overfilled, I suppose with this system it can't really do it, but in a more sophisticated system it might control a drain valve to let the water drain out, or something like that. Or if you think of a motor, you know, it can speed the motor up, it can slow it down, it can reverse it. So the idea is always to try and get rid of this error, make this error zero. And of course you've got two parts to that error. You've got your transient time when the system's changing, and you've got your steady state time when the system stops changing. So anyway, so that's the idea. So what I was going to say, proportional control, you've got your three types. You've got your proportional controller. So if we talk about this output here, for a proportional controller, the output is just a proportional value, a gain value, which is the things you've been setting in your coursework if you've got that far, times the error. So that's for the P type, yeah? And then for the I type, which you would never have by itself, by the way, you always have PI. You would never do I by itself. But for the I type, the output is, should be an I. I think this might be in the slides anyway, but it's the integral, an integral gain term times the integral of the error over time. And then for a D-type one, derivative type, it's the derivative gain times the rate of change of the error. So they all have slightly different effects on what actually happens to the response. I might switch back to the slides because I think some of this is probably in the slides. Save me having to write stuff in. But anyway, so they have different effects, and we can see what the effects are as we go through the lecture. Any questions about that? You've seen this stuff before? A little bit, yeah. That's fine. Is anybody copying that, by the way? Do I need to leave it up for a bit longer? No? Okay, so we've got some examples. I think it's diving in a bit quick here because it's showing you how to actually make the controllers without explaining what they do, but never mind. So yeah, so you can see here, this error is equal to the set point minus the measured variable, or the reference minus the controlled variable. Two different ways of saying the same thing. And the output's equal to the proportional gain times that. So proportional gain for this would be this resistor divided by this resistor times the difference. Well, the gain's actually just that term, IG over R. And that's the error. Okay. So I'll show you how that affects your system output. Generally, we think about second order systems. I think your system is a first order one, the one in your coursework. But it might look more like a second order system when you put the feedback on it. And generally we look at second order systems because first order systems are not that controllable really. Second order systems are the one we're interested in where we might have some overshoot. We might want to change the rise time. You know, none of these things can really be controlled on a first order system. So there's a little example of the limitations of proportional control. Obviously, it's being done with amplifiers or some kind of electronics. So there are limits to how much gain you can actually put into the system. So the higher the gain, the faster it reaches these saturation points. So that's a saturation point, and that's a saturation point. The controller cannot drive any more than these. This is a 4 to 20 milliamp system, obviously. So the bottom limit is 4 milliamps, and the top limit is 20 milliamps. You obviously can't go beyond those. So the higher the gain, the smaller this band is. So you can see, like with a reasonably low gain, you've got quite a big range of values you can drive and quite a large proportional band. But when you put your gain up, you have quite a small proportional band here. And I think it actually works out that the proportional band is 100 divided by the proportional gain in percentage terms, or 1 over proportional gain in non-percentage terms. So you can see here that's with just a gain of 1. You get the full 100% controllability. But as you go up with the gain, your controllability becomes less and less. Okay. So actually on the Bitronic rig, you can see, I think, when you set the proportional gain, I haven't got the rig up here, you can actually see the proportional band. It does actually tell you what that is. So you can see the relationship 1 over the other. So a little example here. So you've got, similar to what you're doing, controlling the level of water in a tank, varying from 0 to 9 meters. If you require 5 meters, close the valve, 5. Okay, so you've got a proportional band of 1 meter as far as I can see here. 5.5 minus 4.5, that gives you a 1 meter band. Yeah, and then quite easy. 1 divided by your total level, which was 9, I think, gives you a proportional band of 11.1%. Yeah, so this is your 1 meter range, and that's the 9 meters total level change you could have. So this gives you a proportional gain of 100 divided by that is 9. It's quite easy. Okay, some examples of how proportional control works. So normally I would just look at that looking at a second order system. So I might just switch back to it's more understandable if you just think of a second order system, I think. So all it's doing is it's increasing the output, essentially. That's what gain always does. Yeah, you multiply anything by gain, it always increases the output. So if you had a sort of system which had an output response similar to a second order system, amplitude on that axis, time on this axis, and maybe a second order response slightly underdamped. Might look something like that. And we're always thinking about step response here in this case. We're not thinking about frequency response with sine waves, impulse response with an impulse, or ramp response or anything like that. We're just thinking of step response. So maybe our reference step input maybe did something like that. Okay, so obviously this is the reference value, or what did it call it? I can't remember what words it might use. But anyway, that's what we want the system to get to. We're maybe just getting that. Of course, if we add a proportional controller with some positive gain more than 1, we might end up getting something that looked maybe more like that. Okay. So some of the key things to note there is this is the steady state error, yeah? So if you increase the proportional gain, does the steady state error get bigger or smaller? Looking at that graph. Steady state errors once it's settled and it's not changing anymore. Is it getting bigger or smaller?
Smaller.
Smaller. Of course it gets smaller. Yeah, you're increasing the gain. You're making everything bigger. So usually we'd have a negative error like that. Yeah, usually your system will give a smaller output than what you want because the loss is in the system. It's quite rare for a system, I guess if you got the gain completely wrong, maybe it would, but it's quite rare for a system to give a higher output. But anyway, increasing the proportional gain will always make the error smaller. We'll call that steady state error, and that makes it smaller. But actually, with disproportional gain by itself, you don't get rid of the error completely. There's always some error left. One of the other things, I think it affects the rise time slightly. The rise time is quicker. Remember, we measure the rise time from 10% to 90%, wherever that would be, maybe that'd be it. Of the final value, which is this value here. Okay, so these are percentages of your final value. So the rise time's a bit quicker. You can see that from the diagram, I think. Yeah, this one maybe takes a little bit longer. I don't know if it's very significant. I haven't said that. So that one might be going from there to there. That would be defined as your rise. So some of the Chinese students were asking me, why do you define, I was teaching them the same subject, why do you define rise time from 10% to 90%? And I'm not 100% sure of the reason, but I think it's because you can get some strange anomalies, I can't even say it, strange things happening at the beginning and at the end of your rise. Yeah, well, maybe the system takes a little while to come on. I think with your system, for instance, you maybe get something that looks like that. I don't know if anyone tried to use the ID data tool and the transfer function estimate tool. I think it gives you a response that looks a bit like that. So you can imagine there might be some sort of strange things going on here, maybe some noise corrupting the signal. So it's not a good idea to try and measure the slope of something where it's not particularly constant. It's better to look at it where it's more constant. And I think for most systems it's going to be reasonably constant between 10 and 90%. But then, of course, it starts to even off at the top as well. So you're not going to measure a good rate of change if you use maybe 0 to 100%. Some systems might not get to 100%. You know, there's a whole range of reasons why the standard is normally 10% to 90% for rise time. And actually that's true for electronic signals as well. And digital signals. If you look on data sheets for digital devices, you'll quite often see rise time specified, and usually that will be 10% to 90% as well. So that just seems to be an industry standard. Anyway, so that's what the proportional control does, and we'll come back to that, see the effect of the other ones. So has anybody actually tuned proportional PID controllers in real life? Any of you do that at all? No? Okay, I thought you might have. Yeah, so this is a bit of an odd picture. I don't know why this low gain one wouldn't still have the same sort of shape. It normally would, but anyway. So, lower steady state error, faster riser and peak times, and higher overshoot. Proportionally, the overshoot's not that much bigger. The higher overshoot's not really a problem for proportional only gain. But okay. And of course, if you make the gain too high, as I said, you get a very small proportional band. Going back to this picture here, if you have really high gain, your system's just going to go from this point to this point, in a very, very short band. So you end up with an on-off controller, which is not ideal. That's not what you really want. You've got to be careful with what you do. Okay, so then we have integral control. There's various different ways of doing this. I would imagine most people would probably do it with a computer nowadays. In fact, have any of you done the micros course? Yeah, so you would have done a PID design using software, which I think would be far more common than using op-amps nowadays. But anyway, you can use an op-amp. This basically is an integrator. It's a mathematical integrator, yeah? It just integrates the signal coming in here over time. And for this particular one, you can see it's got this equation here. But the general equation for an integrator in a PID system is just this Ki integral gain times the integrated change of the error. And you've also got, you'll see some data sheets, you'll see them defined as integral action time, which is just 1 over that. I don't really need to go into that in any great detail, I don't think. So in this case, the output's proportional to the integral of the error over time. So if you remember what an integral is, it's actually adding up the error over the time, yeah? So that's the whole point of doing integration, is to be able to work out something like energy from power, yeah? Or something along that line, so you're adding up over time. So for this, the error is always going to have an effect on the controller. So the controller is always going to do something with the error until the error disappears. Yeah? And the longer the error is there, the more the controller is going to try and drive the actuator to get rid of it. Yeah? Because it's adding over time. So the error is getting bigger and bigger over time. Or sorry, the output from the proportional controller is getting bigger and bigger over time. Because it's trying to get rid of this error that's been there for a long time. So the main thing that the I controller does is it removes the steady state error. Because eventually it will reach a point where the error will disappear, because it will be driving the actuator so hard to get rid of this. The disadvantage is it can cause more overshoot, longer settling time, and possible instability. And I think on the next slide, yeah, and the other big change problem is that it's sensitive to a thing called integral windup. And that is, if you have a big change, you have a big error, the error is there for a length of time, the actuator in the system cannot actually drive hard enough to get rid of that error. So you get a thing called integral windup where saturation occurs here, like this. And the problem with that is the actuator, the controller, if it's a PI controller, it will shoot right up to the maximum that the actuator can cope with. And because that's not enough to remove the error, because the error has either been very big or it's been there a long time before it saw the change, it'll just sit at that and it'll never do anything. It'll never do any control whatsoever. So if you put a flow control system, your valve will just open and stay wide open. If it's a DC motor, your DC motor voltage will go up to its maximum and the motor will turn at its maximum speed and you'll have lost control completely of the system. So the only thing you can do in this case is to reset the system somehow by falsely making the error 0 and then letting it restart looking at the error over time. I don't know, again, with the micros course you might have put in some integral wind-up capability so that it reset the error if it sat at a saturation state for any length of time. Don't know, did you do that? No. But usually it's done in software, because all it requires is for the error to be artificially reset to 0, and then the system can see it again and start to try and react to it. Okay, so just going back to my little diagram, the sort of thing I would say that the integral control, if it's working and not suffering integral wind-up, it's probably going to do something like probably going to have an effect so that the system does something like that. Okay, so this is with PI, and the green one is just key by itself. And the black one's no control. Yeah? So you can see that the effect is probably a more unstable system, certainly. bigger overshoot, fast rise time, but the key thing is that steady state error will disappear if your controller is working correctly. So the key thing with PI is no steady state error. But might not be a great system. Depends what you're interested in. Like a milling machine, you wouldn't want a milling machine to have a huge overshoot. It would ruin your bit of metal. I don't know, if it was some kind of hospital drug dispenser, that would be a major issue as well. The patient would probably die before it settles down. So, you know, they're used for all sorts of things. Some systems might not matter. Temperature control probably wouldn't really matter if it overshot a bit and then took a while to settle. Most people aren't going to really notice a temperature like that, unless, of course, it's maybe some sort of cooling system where you can't allow overheat. So, you know, it does depend on the system, what kind of controllers you need. Anyway, so that's PI. And then the last one's the D type.
Well, if you could create a system
And the main effect of the D type is to counteract the effects of the PI. So you do get proportional derivative controllers by themselves as well, just PD. But the main effect of the derivative type is it kind of, you already know integrals and derivatives are the opposite in mathematics, yeah? So the same here, the derivative counteracts the effects of instability, overshoot, stuff like that. So same idea. With the that's just talking about integral action. You can have a look at that yourself. It's called anti-windup protection. Just by resetting there. But I don't know if that slide's very, honestly. Right, so derivative control, again, you would normally do it with software, but you can make a derivative controller with an op-amp like that, just by swapping the capacitor and the resistor. If anybody's interested in electronics, what you get out, this is a good edge detector. Yeah, because what you get out here is just a little pulse showing you when the edges are changing. because this type of circuit gives you an output that's proportional to the rate of change of input. Okay, so I think there was a student a few years ago was looking at designing a drum kit. So all he wanted to detect was when the stick hit the drum. He didn't really want all the continuous oscillations that you got after that. So something like an edge detector like this was quite a good circuit for doing that, because it just looked at it just gave an output when there was a big change of input signal. But it didn't give an output once the input signal had kind of settled down a bit, or it gave a much smaller output once it had settled down. So that's the idea. So what happens here is the faster the error is changing, the bigger the drive to the actuator, and the slower it's changing, the smaller the drive. So going back to our picture, in fact, it might be. So, that explains it anyway. The faster the error is changing, the greater the control action. It has absolutely no effect on steady state error, because by the time you get to the steady state, your error is not changing. So your derivative control is completely out of the system at that stage. Yeah, it can only see a changing error. Once the error stops changing, it doesn't have any effect on the system whatsoever. The issue with this is, if you think of that, if I go back to my slide. So of course, if you have PID together, that's probably your best response. And for some systems, you're going to have to do that, run out colours, but you can imagine with the PID all together, it's probably going to be maybe something more like that. So, but the issue with PID is, if you can imagine, if you've got like a fairly slow changing signal, I don't know, maybe a signal that's doing something like that, coming into your, well, that would be from some kind of sensor anyway, coming into your system, you would normally get some high frequency noise on that, unless you've designed your system really well. Especially if you're sending it any distance, there'll be some coupling of high frequency noise. So what you actually get is probably a signal that looks more like that. Yeah, and you've probably seen this on scopes, yeah, where you don't very often get a really nice, tight, clean signal. You get one that looks like it's corrupted by that, usually by high frequency noise. Obviously, you do get low frequency, 50 hertz corruption on some signals as well, but generally, RF seems to be more of the issue because it's floating around so much. So the issue here is you can see all these little spikes of very fast changes. So they're going to cause your derivative controller to try and drive the actuator more hard on, yeah? Because they look like, you know, fast changes. You know, a change like that is going to have more of an effect than a change like that on a derivative type of controller. So that makes them quite sensitive to noise. And you've got to be very careful with your filtering and making sure your system, you know, using twisted pairs to get rid of the noise, cross-coupled noise and stuff like that. So that's why quite often you might not see derivative controllers used, and they might just use PI type in noisy environments, electrically noisy environments. That's pretty much PID in a nutshell, really. That's all there is to PID controllers. They're all doing that, and you just add the different bits that you need as you need them. So the next bit is about the Zcritical tuning methods, and I think most of you have probably done this, so I can zip through this quite quickly, I think. So one of the key things with Zcriticals, again, these guys were around about the 1940s, and they obviously came up with quite a good method, because it's still used to this day, and I think because it's quite an easy method, and it does give a fairly consistent response, system response to a step. But it's not ideal. It's not necessarily what you really want, because what it always gives is this quarter amplitude response, if you've done it correctly, which is not great, because it means you've got this overshoot type response, which might not be okay for your system. You might not want any overshoot. And this first peak is always 4 times the size of the second peak. Yeah, so it's a consistent step response. It's good, you know what's going to happen, but it might not be good enough for you. So actually what we're going to look at in coursework B is a better way of tuning, but it's a very mathematical method. In coursework B, what we do is we've got a specification. How much overshoot are we allowed? How much steady state error are we allowed? What peak time? How fast do we want the response to be? And we can set these values and we can tune accordingly. So this is obviously better. Because if you want no overshoot, you can tune for that. If you can tolerate 10% overshoot, you can tune for that. With this system, you always get the same, four times the peak of that, always the same. Anyway, 2 methods of getting that response. Process reaction method, it's where you've got an open loop system. So it's all very easy in Simulink. You can just take wires in and out of the system. But in real life, you might not be able to open your loop easily. If you think of something like maybe an oil pipe system, an oil flow system, to open the loop there, you're going to have to actually physically take the system apart, drain it. Could be hazardous chemicals. So it's not always possible to open the loop the way you can just remove a wire in Simulink. So for that reason, there was another method they came up with, which was the ultimate cycle method, which is a closed loop method. The disadvantage of that is you have to make the system unstable to get the tuning parameters. And again, I told you already, unstable systems can be quite damaging in terms of wear and tear. Some systems just can't cope with being unstable at all. There might be some severe issue. Obviously, if you're driving anything with the system, you're going to have to shut that down. So there's a couple of problems, but these methods are still used nowadays. So I think the key thing in terms of your coursework is this is what you're trying to get out. This is what your closed-loop tuned PID system should be giving you. Of course, if it doesn't, you can explain why not. You don't need to spend hours and days trying to get it to exactly do that. But it should be something a little bit similar. And as I say, you can evaluate why you think it's not actually working if it isn't working, rather than spending hours trying to get it working. Right, so 2 methods. The first one is you measure the gradient. So this is the open loop system, yeah? So this is like the initial step response signal output you saw, yeah, when you plotted it. You plotted it with the measurement data values, and you've also plotted it with your model, what your model's doing. So we're working on the model now, so we'll think about the model, not the measurements. But anyway, you should get a system that looks like this. You've got some time where it's kind of flat, which is your transport delay block. Most of you should have put that in. And then you've got a sort of first order type of system rise that looks a bit like that. And the idea of this is you measure, first of all you measure the dead time. I think we already know that from the data anyway. and then you measure the time from 0 to 63% of the final value. Which is essentially can give you this gradient if you know the amplitude of this step here. So the gradient is just that value divided by the time it takes to get from 0 to that point, that 63% point. And then you've got a table here where you can put these values in and calculate what your PID controller should be set to. A is the size of the step, so that's the amplitude of step, which in your case will be 8, I think, for most people, unless you've used 80%. R is the slope of this part of the curve, just between 0 and 63% of the final value. And TL is your lag time. So you can get some values here using these equations. You will see some other tables. Some people do it differently. I'm not sure which exactly was Ziegler-Nichols method, but these numbers seem to work quite well, so we'll stick with them. Right. So there's an example here. So a step input of 5. Your output is going from 0 to 10. The 10 must be the 63% point of the output, so I'm not sure what it's actually going to work it out. Because that should be 0.63. So you've got lag times 5 seconds. You can measure all that from the graph. Lag times 5 seconds. Slope to 63% is 10 divided by 40, which will be that. Amplitude 5, and then you just put the numbers in. I don't think I need to go through that. That's quite straightforward. You can do that. And then you've got the closed loop method, which actually I think for your coursework works a bit better. So if you found your open loop method didn't work, you can try the closed loop method and see if you get a better answer. And of course, if you've done both methods, put them in your report anyway. Yeah, don't just put the one that works. I want to see how much work you've done. If you've done extra work, add it into your report. Anyway, so your closed loop method tends to work a bit better. The way you do that, you set your Ki and Kd to 0, and then you gradually increase your Kp value or your P value on Simulink. PID, gradually increase that until you get an output that's sitting constantly oscillating. So essentially it looks like an undamped output. And then you just measure what value of Kp did you have to set to get that, and what's the period of the oscillations. And you just use these values. So the time constant is called the critical time constant, the Kp is called the critical proportional gain, and you just put the numbers in. Quite easy calculations there. So has anybody done it this way? You all did the open loop method?
Yeah.
Those that have done it. Okay, I think this method works slightly better. As I said, the only problem with this is if it was a real system, you might have an issue with it oscillating like that. It's not very good for the system. So that's just an example. I don't think you really need to. So that's talking about proportional bands. So 1 over proportional band will give you, 100 over 4. Gives you proportional gain. To cause the oscillations, time constant, you just put the numbers in. That's not good. And you're always doing PID, by the way, for your system. You don't need to do PI or just P. Just go straight for the PID. So there's some issues with it. Obviously, you've got overshoot. It's quite a precise tuning method, so if anything changes, you could get it becoming unstable. I don't know about poor response to large dead time, that might be true, I'm not sure. And so we're going to look at this cascade method as well, just as in give you some other options. Okay, that's all. That was all I was going to do today. So do you want to just get on with your coursework now?
Yes.
Again, leading up to the exam, there will be some questions. We'll have a look at the... Get this to work. There'll be like your normal weekly questions. That's more important as you lead up to the exam. Make sure you keep up with those questions. I think they'll probably be out. I'm not sure. Let's have a quick look. week 5 notes. So it'll be the week 5 question. Oh, of course not. Self-assessment questions. Okay, none. Okay, there's none this week, so that's good news. Just work on your coursework. Okay, so that's the end of the lecture for anybody listening in. I'll post this tomorrow or as soon as I can. Hope you see you next week. Bye.
This call has been disconnected. Thank you for joining.